Hey everybody, this is Mr. Bortnick for Pre-Calculus. We are in Unit 6, Right Triangle Trigonometry, and today's lesson is topic 6.1.3, which is on inverse trigonometry. You should have some notes that your teacher has given you to work with for today, and you might want access to a graphing calculator. Specifically, we're going to be going over some tips and tricks using a TID3 or TID4. Enjoy today's notes. Welcome to 6.1.3. We're talking about inverse trigonometry. We're going to start this lesson with a quick recap from section 6.1.2, where we were focusing on right triangle trigonometry. One of the big things that we talked about was that if we have an arbitrary right triangle, which I'll just draw here, we can always label our right angle, our 90-degree angle, with this little box in the corner. And what we do is we can label an angle that we don't know using this symbol, which is what's called a theta. So a theta is a symbol that represents an angle that we don't know. So it's an angle that we do not know. And generally, we can label a right triangle a couple different ways using some things that we know from geometry. Specifically, we label our angles using capital letters. So for example, I'm going to label this A, B, and C. And we label side lengths across from those angles with the same letter. So because this is our angle A, if we go opposite it, we would call this our side length A. Notice I'm using a lowercase letter to represent that side length, while the capital letter is our angle. Similarly, if this is our angle B, if we go opposite that, that would make this lowercase b for that side length. And similarly, our capital C, if we go opposite that, is going to be our lowercase c for that. Having this naming convention is really useful as we get further in this chapter with some of the equations that we're going to be using. But one of the ones we focused on pretty much immediately, which is useful for right triangles, is our Pythagorean Theorem. Specifically, that we know the relationship between these side lengths is a squared plus b squared is equal to c squared. Key piece of information when you're using this equation is that your A and your B are legs of your right triangle, while your C value is your hypotenuse. And we remember that a hypotenuse is always the longest side. So our hypotenuse is always the longest side of our right triangle. And if it's not labeled for some reason, it's always the side that's across from the right angle. So that is a very easy way for us to tell. Now, beyond our Pythagorean theorem, one of the things that we talked about is that we can use ratios of sides to describe our angles. We learned about this thing that was called SOHCAHTOA, which is a shorthand way for us to remember what our three basic trigonometric functions are and what their relationships are in a right triangle. This SOHCAHTOA is represented as sine of our angle, theta, is equal to the opposite over the hypotenuse. That's our SO. Our ka represents cosine of some angle is going to equal the adjacent over the hypotenuse. And our toa is tan of theta is equal to opposite over adjacent. We can find these three trigonometric ratios, sine, cosine, and tangent, if you have the sides of a right triangle. One additional thing that I want to mention, we talked about how to find the hypotenuse, but looking at these ratios, we notice that some of them have opposites and some of them have adjacents. How do you figure out which one is which? Well, the word adjacent, one thing I'll mention for you is that the word adjacent means next to. It means next to. So when I'm talking, if this, in this particular picture that we've got here, if this is my angle theta, we already know that this C value is our hypotenuse because it's the longest side, but our B value here, because it is next to our angle, would be our adjacent in this picture. This would be our adjacent, and that would mean that across from it or opposite from it would be our A value. So that would be opposite for that particular angle. as you're working through problems with sine and cosine and tangent, it's really important for you to label your triangles, figure out what your hypotenuse is, figure out which side is next to it that's not the hypotenuse, call that the adjacent, and then your remaining side is the opposite. That's pretty much our recap of 6.1.2. You can pause here if you need to catch up in terms of notes, but we're going to move on to 6.1.3 now. So for 6.1.3, again, inverse trigonometry is our focus. The question is, what is the measure of theta in the triangle below, and how do you know? So we notice that this is a triangle that has two legs that are both 5. It has a 90-degree angle here, and we're trying to find theta. Two nice facts from geometry can help us out in this problem. The first of which is that there's this thing that's called the triangle angle sum theorem. So the triangle angle sum theorem, which is a really fancy way of saying that all angles in a triangle add to 180 degrees. So they always add to 180 degrees. So that's a really nice fact that can help us out in this problem, really in any problem, that you know that if it's a triangle, that those angles have to add up to 180 degrees because of the triangle angle sum theorem. Now, another fact that's actually really useful for us in this problem is a fact about isosceles triangles, which this triangle is a special, it's not only a right angle, but it's isosceles because we notice that this side length is equal to this side length. One of the properties of isosceles triangles is if the two sides are equal to each other, that means that their base angles have to be equal to each other as well. So if this angle here is theta, then that actually means that this angle right here is also theta, whatever that is. So what I'm going to do is I'm going to take these three angles and I'm going to add them up, and we know that they have to add up to 180. So our right angle, that's 90 degrees, plus whatever theta is, right? So 90 degrees plus whatever our theta is, plus the other theta has to equal 180. What we can do is we can combine our like terms and try to solve for theta here. We can subtract 90 from both sides, so theta plus theta has to equal 180 minus 90, which is 90 degrees. And we notice, hey, if we're combining our like terms, the theta is a variable, and there are two of them. So two thetas have to equal 90 degrees. In order to get that theta by itself, because we're multiplying by 2, we can divide by 2 on both sides. And that tells us here that theta would have to be 45 degrees for this to work. Now, in this particular problem, this was set up in a way that we could do this without needing trigonometry. We're able to use some information from geometry, specifically this triangle angle sum theorem, and this special fact about isosceles triangles to help us solve and find the angle in this problem. However, not all problems are going to be like this, right? We're going to have problems if we look further on that don't have this special property about isosceles triangles, and we can still actually find the angles in this case, but we need to bring in a special trigonometric function to do it. So we're going to move on to this next piece. It says, since the sine, cosine, and tangent ratios of a given slope angle are constant, we should be able to find out the slope angle, find out any slope angle is, find out what it is, when given a ratio of side lengths. So specifically, for this box, when we start with a side length, and solve for the angle, this is called inverse trigonometry, which is the title of today's notes. So again, our statement that we've got here, if you are starting with a side length and you're solving for an angle, this is what's called inverse trigonometry. Now, this is different from our last lesson where we were given side lengths and we were trying to use those to find a particular ratio using that SOHCAHTOA that we talked about earlier today and in yesterday's or previous lesson. But here we're going to introduce some new trig functions that are related to the old ones in that they are inverses of the previous ones that we knew. So inverse sine has a symbol that is on your calculator that is written like this. It's got a sign with this little -1 like an exponent. So inverse sine of a particular angle. This is to represent that it is an inverse, which means it cancels a sign out if we use it in an equation. I'll mention for those of you who might be planning to study higher level math, sometimes this is also referred to as an arc sine of an angle. Those mean the same thing. Similarly, the inverse cosine, if we were to do that, is this cosine with this little -1, inverse cosine of an angle, and that can also be called the arc cosine of an angle. Depending upon the context of a problem or what you might be working on, you might see it written in one way or another, but they mean the exact same thing. And then our third one is the inverse tangent. So specifically here, that is the inverse tangent, tan to the -1 of our angle, which is the same thing as arc tan, if you were ever to see that. So those are three basic inverse trig functions. We're going to talk about how they get used, but in general here, we can take a look and we can notice here that in this particular triangle that we've got, we have an angle and we've got one leg, which is 12. We've got a hypotenuse, which is 13. And for problem number 5, it says write an equation to solve for angle B using the trig function of your choice. Now, we could use any of the three of these triangles in order to find the angle. These are actually all three the exact same triangle. So we're going to start with just sort of our first equation that we've got here, this arc sine. I want to show you how that gets set up. Now, the way that we would think about this specifically is I'm going to start with what we know from our previous lesson. Specifically, if I were to label this triangle of what I've got here, we notice that across from our right angle is our hypotenuse, and next to our angle B that we've got here would be our adjacent, which means that across from our angle theta would be our opposite. So what I notice is that in this picture I was given the hypotenuse and I was given the opposite. Now, if I ever needed to find the adjacent, whatever this side length is, we know that we could always use the Pythagorean Theorem to find that third missing side, as long as it's a right triangle. In this case, we can actually see from our other pictures that that side length here would be 5. And if we did the Pythagorean Theorem, we could find that as well for this. But since this picture here is giving us an opposite over hypotenuse, I want to think to my SOHCAHTOA from our previous lesson. I want to think about which of our three trig functions, sine, cosine, or tangent, involve an opposite and a hypotenuse. Well, specifically here, I notice that there's an opposite and a hypotenuse for our sine function. And so I'm going to start with that equation that says that sine of whatever our angle is has to equal the opposite over the hypotenuse. That is the SO part of our SOHCAHTOA. And so if we plug in what we've got here, well, we know that our theta here is the angle B. So we can say that this is sine of our angle B has to equal the opposite, which is 12, divided by the hypotenuse, which is 13. 12 over 13. Now, I want to find angle B. That's the goal here. I don't want to get this B by itself. But this sine operation is doing something to it. So what we need to do here is we actually need to we need to think of what's going to cancel the sine out in this equation. And that's where the inverse sine comes in. What I'm going to do is I'm going to take the inverse sine of both sides of this equation. So notice I'm taking the inverse sine of both sides of this equation. What's inside of these parentheses? Well, that's the sine of B that was there, and this is the 12 over 13 that was here. So I had sine of B, I took the inverse sine of the left side of the equation, and that's equal to the inverse sine of the right side of the equation. I need to do this on both sides of the equation to keep it balanced, but here's the trick for this. Because I've got sine and inverse sine next to each other, and their inverses, that is going to cause these two functions to cancel each other out, the sine and the inverse sine, because they're inverses of each other. And that gives me here that B, my angle, has to equal the inverse sine of 12 over 13. So that is going to be equal to the inverse sine of 12 over 13. What we're going to do now is we're going to switch over to our calculator, and we're going to show how you can find this on a TI-83 or TI-84. use the calculator, specifically a TID3 or TID4, in order to find inverse trig functions. Now, what I'll mention first is it's really important for you to make sure that your calculator is in the correct mode. You can do that by clicking this button that's right here that says mode, and you want it to be in degree mode, because when we're talking about triangles, we're talking about angles generally in degrees. So what I'm going to do is I'm going to scroll down and make sure that degree is highlighted. My calculator was in radian mode, so I'm glad that we checked. To get back to my main screen, I can then hit second and then quit to bring me back to my home screen. Now, we know from this chapter that we can use sine and cosine and tangent in order to find any of those values. But what you might not have noticed when you're using your calculator is that right above those are actually our inverse trig functions. We can see that there's an inverse sine, an inverse cosine, and an inverse tangent. So for this particular problem, we wanted to find the inverse sine of 12 over 13. So what I'm going to do is I'm going to hit second and then sine, and then say that I'm going to do the inverse sine. We notice it's got that little -1 to show that it's the inverse. And we're going to say that we're doing 12 over 13 inside of that inverse sine. If we hit enter, this calculates the degree that that angle is going to be. And so in this case, angle B here would be 67.38 degrees if we're rounding to 2 digits after the decimal place. Now again, the way that we did that is we hit second and then sine, and then we put in our 12 over 13. Now again, we can do this with any of our other inverse trig functions. I can hit second and cosine to bring up inverse cosine if a problem needs that, or I can hit second and tan to bring up inverse tan if a particular problem needs that. We're going to head back to our main problem, and let's do it. All right, welcome back. We just used our calculator to show that the inverse sine of 12 over 13 is equal to about 67.38 degrees. Now, before we move on from this problem, I just want to emphasize that we could have actually found angle B from using any of these three triangles. Specifically, I'll just mention, we could have used the second triangle here because we had an adjacent and a hypotenuse. We could have said that cosine of B would be equal to 5 over 13. If we used the information from that triangle. Or we could have used this third triangle, and since we've got an opposite and an adjacent, we could have written an equation that was tan of our angle B is equal to 12 over 5. Now, similar to our problem here where we had the sine, to get rid of the sine, we brought in an inverse sine on both sides of the equation. We could do the same things over here for these two equations, except we would need to make sure that we're using the correct inverse. So because this is cosine, I would be using inverse cosine on both sides to cancel it out. Similarly here, because this is tan, I'd be using inverse tan here on both sides to cancel that out. Great. Let's talk about number 6. So for the triangle below, find the measures of angle A and angle B using inverse trigonometry for both. So we're going to start with angle A. This is our angle A that we've got right here. And we see that we've got one leg, we've got one hypotenuse, and we're missing our side over here. Now again, if we needed to, we could use the Pythagorean theorem to find that missing side. But actually, I can find both of these angles without needing to do that. So I'm going to show that here. So since we're working with angle A first, I'm going to label that as my theta. That's the my stand-in for the angle that I'm trying to find. Now, as I'm looking at this triangle, I notice that my 15 is across from the right angle. That's the hypotenuse. And that my 14 is next to my angle theta. So that means that this is my adjacent. So if I'm thinking again of my three trig functions from SO, CA, and TOA, we notice that the only one that has adjacent and hypotenuse is that middle one. It's that cosine. So I'm going to write out my equation. Cosine of my angle theta is going to equal the adjacent over the hypotenuse. From there, we plug in what we know. Well, that theta is angle A, so we're going to label that as A. And our adjacent is 14, and our hypotenuse is 15. Similar to the last problem, we want to get this A out of the cosine. So in order to do that, we need to do the inverse of whatever trig function is there. In this case, that is cosine. So what I'm going to do is I'm going to take the arc or the inverse cosine of both sides. Just setting that up here on both sides. And notice that the two sides are staying the same. Everything that we've got is staying the same inside of these parentheses. I'm just adding the arc cosine or the inverse cosine on both sides. Now again, similar to our last problem, because these are inverses, this cosine and inverse cosine, they're going to cancel each other out on the left side of this equation. They're going to go away, giving me that just A is equal to the arc cosine of 14 over 15. Take a moment with your graphing calculator or calculator to try to find that arc cosine. If you do that, you should be getting that this is about 21.04 degrees. So if you need to pause the video in order to do that, you are welcome to do that here. But again, you should be getting 21.04 when you do that in your calculator. Really quickly, if we want to find angle B, I'm going to erase what I've got here on my triangle, and I'm going to relabel my angle B as my theta. Now my 15 is still a hypotenuse in this problem, but now my 14 is across from my theta. So that means that this is now an opposite for my angle B. Again, thinking back to my three trig functions that I've got here, the only one of these three trig functions that has an opposite and a hypotenuse is going to be sine. So I'm going to use sine of theta is equal to my opposite over my hypotenuse. If we plug in what we know, we're talking here about angle B, and our opposite here is 14, and our hypotenuse here is 15. We can take the inverse sine of both sides. If we do that, that inverse sine is going to cancel the sine on this side, giving me that B is equal to the inverse sine of 14 over 15. Yes, here I did skip a step of showing that work of taking the inverse sine of both sides, but again, we know that the inverse sine is going to cancel the sine on the left side here, and the inverse sine is going to still be on the right side. Once again, though, if we wanted to find this, we can plug this value into our calculator, the inverse sine of 14 over 15. If you need to pause the video, you're welcome to do that, but when I did that, I got that this is equal to about 68.96 degrees. So I would say those would be my two answers for this problem, that my A is equal to 21.04 degrees, while my B is equal to 68.96. I'll also mention, just as a side note for this problem, we could have saved a little bit of time in this by using our triangle angle sum theorem. Once you've got two angles in a triangle, you know that you can add those two angles up and subtract from 180. And that might be a little bit faster in cases like this instead of using an inverse sine, but it would get you the same answer either way. What I'm going to ask for you and your teams to do is to move on to number 7 as some practice problems. If you need to pause to work through that, I think that would be great. But what I'm going to do is I'm going to actually just display the answers for these, and then you can check in with your teacher in terms of finding some work. So for 7a, I got that this one was equal to 60 degrees for our missing angle. I got for B that this is equal to 45 degrees for our missing angle. And then for C, I got that this was about 28.57 degrees. So those would be the three answers that I'd be looking for as you're working through. See if you can figure out the inverse trig function that you'd need to use and to work through that. Have a great day. Good luck on your practice and your assignment later. Take care.